So, dear all, it is indeed a great pleasure for me to welcome you to this year's Bireland Lecture event, where we have gathered scientists, researchers, and others with great interest in astrophysics, geophysics, and space research to honor the great Norwegian scientist and entrepreneur Christian Birkeland. This is a collaboration between the University of Oslo, the Norwegian Academy of Science and Letters, and Yara International, and the Bireland Lecture has been held since 1987. Later, the Norwegian Space Center also became a partner in this wonderful collaboration, and since 2012, an introductory lecture related to research and innovation has been added to the lectures. Christian Birkeland was a Norwegian mathematician who became interested in theoretical physics and experimental physics. He did groundbreaking work in the understanding of phenomena in space, both around the northern lights as well as other conditions. He is particularly known for his studies of the northern lights, for which he was nominated the Nobel Prize a total of 7 times. Birkeland's aurora research was ahead of its time, and not until modern satellites and space probes could be used for measurements were his theorems confirmed. The existence of the magnetosphere around the Earth is also one of Birkeland's early theories. Birkeland describes solar storms and that a large part of the universe is invisible interstellar mass. Theory have also been confirmed in recent times. Today, Birkeland is considered the first space scientist, but in his time, his theories were refuted by many leading scientists. Today, we will learn more about Birkeland's legacy by the dedicated Bireland Lecture, but first we will have an introduction lecture given by Gunnar Maehlum. Gunnar Maehlum is the Chief Executive Officer and Integrated Detector Electronics. He holds a PhD in physics from the University of Oslo and has a broad background from position at CERN, the University of Karlsruhe, and the University of Perugia. He joined IDEA's ASA in 1997, where he worked in technical, scientific, and management positions. Prior to his current position, he has been Vice President of Research at Gamma Medica and General Manager of Gamma Medica IDEA's Norway. So the title of his lecture is An Age of Discovery in Gamma Ray, High Energy Astronomy and Planetary Science enabled by observatories orbiting Earth and the other planets in the solar system. So please.
So it's easy to forget that we are actually living in an age of discovery, but with, from Hubble and through a lot of other less known missions, an enormous amount of discoveries has been made in the universe. And I will talk now I have selected a couple which relied on our electronics to do what they achieved. So one is quite interesting, and it's only 1 year ago. There was an enormous explosion quite far from here, about 2 billion light years. The gamma ray burst is actually a typing mistake there because it's 2022, 1009. And this was the most powerful explosion ever seen by any man, live or dead. And it was, unimaginable large. I cannot verify these numbers, but we talk about 10 to the 48 joule. This is supposed to be like if you would convert the sun 5 times into energy in one go. So it's beyond any imagination. And what was also interesting is that, Birkeland, he was an atmospheric scientist, and this gamma ray burst was so strong that it actually ionized the Earth's atmosphere, and it was visible in sensors that are not made for astronomical observations, but in radio transmissions. I don't think that has ever happened before. So this was done by a NASA mission the Swift Space Telescope. This is a mission which has been in orbit now for almost 20 years. And our humble contribution to that mission is an integrated circuit that we delivered a few years before the mission. And the signals from the gamma ray burst, before they were detected by any people, had to go through the transistors of that circuit. So this is, I think it's quite fun to think about that. This is the circuit. It's only about this size. It's mounted on a module, which is again in the spacecraft. There's actually a few hundred of this, and the imaging there was done using a coded mask, which is quite different from a telescope, because you cannot image gamma rays with lenses or mirrors. I cannot go into any details here, but it was a huge array of these crystals, cadmium zinc telluride crystals connected to the ASIC that actually detected the first signals from the gamma ray burst. Also, there's a couple of other telescopes here. There's a UV and visible and an X-ray telescope that complements the gamma ray detection capability. So this is the kind of our first contribution to a large scientific mission. And it's also quite great that after 20 years, the spacecraft is still in operation and delivering very good data. Also, this was, of course, seen by the James Webb. I don't have a very impressive picture, but this was one that I found online, showing the afterglow after this explosion. Because almost all observatories in Earth and in orbit was actually directed towards this area after it was discovered. Because everybody wanted to know what's this. And also it was seen in other observatories in orbit that is actually also using our ASICs. The HXMT is a Chinese, Agile is an Italian, and the SRG ART-XC is a Russian mission. Okay, so back to the company. So what do we do? So the company, we develop and manufacture electronics. More particular, integrated circuits like those that you see on this picture. Each of these circuits contains literally many thousands and 10,000s of transistors. And by combining them into various functions, we can amplify the signals from the sensors. We can process the signals to some extent and deliver them to the onboard computer. They are downloaded to Earth and then analyzed by the scientists. In this activity, these are some of the people. We need, of course, to use a lot of machinery and equipment. So this is typical activities that we do. These are testing, 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 and this is showing off to customers. The company is located here in Oslo. We are at the top floor here in this building. So we were actually founded as a spin-off from high energy physics at CERN. So actually a friend of mine founded the company. I was not part of the founders, but I came in at a later stage. So in addition to, of course, the science and the astrophysics, we also supply sensors, detectors to medicine, biology, and high energy physics applications. So we have been around for 30 years, more than 20 missions, and more than 20 different instruments. So this is an extensive list. I don't know how much time I'm using because I don't see the clock here. If time allows, we have talked about the Swift. I wanted to show a few selected missions, 5 in total. We see here some of the circuits. We see some artist drawings of some of these missions. So the next one in line is the AMS. This is, I think we skipped this very fast. So essentially there are 3 types of missions that I talk about: gamma ray, cosmic ray particles, and planetary. But let's go quickly, and I will skip this because I think time does not allow. One reason to put observatories outside the atmosphere is, one thing is, of course, you get rid of the distortions from the atmosphere. The other one is that a lot of radiation, actually most of the radiation that you want to look at, is absorbed by the atmosphere. You see here, all this is X-ray and gamma ray. Visible light gets through. Infrared, some of it gets through, but immediately when you get to maybe 15, 20 micron, you are blocked again. So that's why you have to put the James Webb in space. Then again, at the radio area, there's a nice opening, so we can do that from ground. But X-ray and gamma rays has to be detected from space. And all the objects emit in essentially the whole spectrum. These are just some examples from our neighbor, very large galaxy. If our eyes would be a bit more sensitive, we would see it as an enormous object on the sky, larger than the moon. And also there's a zoo of objects in the gamma ray and X-ray that can be observed. So these are all renderings, drawings, because this is not visible to our eyes, so it's kind of difficult to, we don't really know how it would look like. So we have to make kind of fantasy drawings of some of it. Some can be an image, but all of this is actually a gamma ray map of the moon. And the sun also emits a lot of X-rays. Yeah, so this is the AMS mission. That's a huge mission on the space station, about 11 years in orbit. So we delivered A6 for this instrument here. That weighs in at around 7 tons. So it's many layers of silicon detectors that tracks the cosmic rays through the detector. There's a magnet, and in this way you can measure the momentum. And there's also other detectors here, so you can analyze what particle it is. And this is it's essentially a CERN detector, a particle physics detector put in orbit. They have recorded several 100 billion cosmic rays over an 11-year period. They have hundreds of antiprotons. Antiprotons are there, but they also, which is quite interesting, they have a handful of helium-3, anti-helium-3 candidates. If that's a fact or not, we don't know. That is up to analysis. But if anti-helium-3 exists, that's a huge discovery, because that means that there is something, our understanding of the matter-antimatter balance in the universe might be different than what we think. So our contribution here was integrated circuits that was placed at the end of these large ladders of silicon detectors. This is a project we did together with the University of Bergen to look at, they wanted to look at gamma rays coming from lightnings. This is also quite an interesting discovery, because nobody expected that lightnings could create X-rays and gamma rays, but they do. It was discovered in 1992 by the NASA spacecraft, and then Nikolai Østgaard and another scientist in Bergen, they constructed a detector, and this is actually a whole Earth image, and you can see some gamma rays emanating here from an area in Borneo of a thunderstorm. This is, they have had some international notability with their results, and that's very good to see for us that they are successful. Our contribution here is some small parts there that sits inside this one, which sits inside this one again. So the devil is in the details. Yeah, this is another contribution that is quite recent is to the Jupiter Icy Moon spacecraft that was launched now in April. That's a huge spacecraft made by ESA, European Space Agency, that will arrive at Jupiter in 2031. It will orbit Jupiter and the moons, a lot of flybys of the moons, and investigate conditions on the icy moons, which, as we know, might harbor or have conditions that could harbor life. So our contribution there is to an instrument called the RADEM. Is this one? it means the radiation-hard electron monitor. It actually detects more than electrons. It also detects protons and ions. It's a box about this size, which is mounted on the outside of the spacecraft. This is taken from the inside of the spacecraft, looking outward, so you see the backside of this. And then electrons and protons they slam in through these holes, and they are detected by silicon detectors that are made by SINTEF here in Oslo. Then I got that also, which is quite nice. So there's a good Norwegian contribution there. And our ASIC here reads out the signals. Yeah, it's a very complex travel to get there. And they have turned on the instrument, and it's working, and it will actually be turned on for the whole duration of the mission, not only at Jupiter. So it will also be used to monitor the environment around the spacecraft. Then finally, we have a Norwegian activity on the particle detection. Space Norway is launching next year 2 satellites for broadband communication in the Arctic. They will have a peculiar orbit, low in the Antarctic, high in the Arctic, to give almost stationary coverage. And we are so lucky that we have been allowed to put on a detector on one of these spacecraft to monitor the radiation around the spacecraft, which will also pass through interesting areas around the Earth, because it goes from 40,000 to 8,000, 40,000, 8,000 kilometers. So we'll have a nice mapping of electrons and protons in that area. So this is a mission which is led by Space Norway. ESA is involved, and the Norwegian Space Agency has kind of been the big sponsor of this. So we can see that they kind of give almost stationary coverage there in the north. It's nice to be able to put a scientific payload on a kind of national security and commercial satellite. So this is what we have made. So we did everything in-house, except the mechanics, which were developed by the Norwegian Defense Research Establishment, FFI. They actually engineered and designed the mechanics for us. We did all the electronics and the software, assembling everything. And this has led to another nice activity, which has just started. We will deliver 6 similar units to the Galileo second-generation satellites. This will enable a constant monitoring of electrons, protons, and ions in the 22,000 kilometer orbit that these satellites have. So we will deliver 6 units, optionally 4. And here we have good help from Kongsberg Space Electronics in Horten, which will do all the manufacturing, assembly, integration, and test for us, which is quite nice. This is just a rendering. Finally, this is a bit, the text here didn't come out right. We are also working on infrared detection. This is a circuit that we have developed, which is quite similar to the circuits that is used in the James Webb telescope, called the sidecar. This is an European version of this, and it can be used to read out infrared sensors in huge telescopes. Unfortunately, I don't know what happened with the text there, but something got lost in translation. This we hope now first to get on the Copernicus missions to observe the Earth, climate change, temperatures, gases, and so on in the atmosphere. But it could also be used in an astronomy, astrophysics mission, if somebody wants to use those ASICs. And finally, with some scientists at the University of Oslo, they propose a lunar orbiting instrument to measure the neutron lifetime. On Earth, the neutron is measured 2 different methods. They all have very small errors, but they differ in value. So there's a conundrum there. I don't know so much about this. There are people here in the room that knows much more than me. And we propose to use some of our electronics to fly it around the moon and see if we can have a third independent measurement without any matter close to the neutrons. So this discrepancy points to possible new physics, which, yeah, if it's there, it's great. If not, okay. So we call it the compact lunar gamma spectrometer. It's also a version is also made to be put on a rover on the moon to look for water, do elemental analysis on the surface of the moon. There we work with the University of Oslo, the Center for Space Sensors and Systems. And yeah, there are people in the room here that work on this. Okay, this was all. I hope I kept my time.
So Birkeland was a great inspiration, and many of his young assistants later become physics professors. Several of them worked in astrophysics, so that these academic circles continued to develop after his death. Birkeland was a visionary scientist with the ability and commitment to carry out large-scale projects in the laboratory and in the field, to follow up on theoretical studies and to see the application of his research. In the spirit of Christian Birkeland, Yara has decided to honor great young scientists by financing the Yara Birkeland Award in Physics and in Chemistry. And to hand out the prize, I give the word to the Vice President of Yara Technology, Per Knudsen, and Professor Emeritus Per Amund Amundsen, University of Stavanger.
Thank you very much. Dear Laureate, Dean Professors, ladies and gentlemen. Every year we celebrate and remember Christian Birkeland by handing out the Birkeland Award, an award named after a remarkable scientist given to another remarkable scientist. In Yara, we are extremely proud of our heritage. The science of Christian Birkeland led to what is called the most life-saving innovation ever, mineral fertilizer. Billions of lives saved. But it wasn't mineral fertilizer that Birkeland started out researching. That was a byproduct. Christian Birkeland's passion was Aurora Borealis, the northern light. He organized several expeditions to Norway's high-altitude regions, where he established a network of observatories to collect magnetic field data. He was the very first scientist in the world to realize that the northern lights had something to do with the electromagnetic storms from the sun. And this led him to invent the electromagnetic cannon that enabled the making of fertilizer by harvesting nitrogen from the air. I'm sure Birkeland himself would have been very enthusiastic if he was here tonight. It would have been right up his alley. Because, like him, this year's laureate has studied magnetic fields, but have clearly expanded the area to study. While Birkeland focused on the sun and electromagnetic storms there, this year's winner have looked at magnetic fields, well, everywhere. At least that's how I understood it. I'll come a little back to the details, but I think we will have the jury's basic for decision.
This year's Yara Birkeland Prize for 2022 actually is awarded Dr. Robert Bleckert Nils Håkan Wissing for the best PhD in physics awarded at the Norwegian University in 2021 to 2022. The title of the thesis is Simulating Galactic Dynamo Processes with Smoothed Particle Magnetohydronamics. It was defended for the PhD degree at the Institute of Theoretical Astrophysics at the University of Oslo in September 2022. His supervisor was Professor Sijing Shen. This is a thesis in the field of computational physics, focusing on magnetohydrodynamical computations of galactic magnetic fields. Such calculations are notoriously challenging because the description combines the electrodynamical Maxwell equations with the nonlinear basic hydrodynamic equations applied to a plasma, which produces a system of coupled nonlinear partial differential equations. These equations, such equations, have solutions which describe phenomena which are very often physically unstable or marginally stable, like turbulence in a magnetic plasma. At the same time, the numerics are plagued by challenging unphysical instabilities. Wissing and his co-workers have developed new, smooth solution methods with very improved dynamical stability properties for calculations of magnetic fields in cosmic objects. In 3 papers, all published, are these methods applied to calculation of turbulence in ionized accretion disk around black holes in galactic nuclei, including quasars, and on calculations of the dynamo effect which generates the magnetic field of a galaxy. The study of galactic dynamics has come in focus with the later words explosive development of new observation methods and equipment of the young universe. For example, the James Webb telescope, and we will hear much more about that later today. Some of the largest challenges in understanding is precisely here the descriptions of the dynamics of the galaxy, the magnetic fields of the galaxies and the black holes. And Wissing's thesis represent valuable contributions to understanding and this type of dynamics and being able to do the calculations correctly. Wissing's thesis represent basic research at its best, and it can very safely be said to be in the spirit of Christian Birkeland. Both have even studied how magnetic fields create spectacular cosmic phenomena. Birkeland figured out how the aurora borealis and also the aurora australis, of course, is created when charged particles from the sun are deflecting the Earth's magnetic field. While Wissing has calculated magnetic field in galactic nuclei with massive black holes, which deflect charged particles in the accretion disk and focus them so that on jets emerging from the poles of the black holes, which forms quasars with their remarkable properties guided by the magnetic field. So, congratulations to Dr. Wissing.
So, Robert Bleckert, Nils Håkan Wissing, on behalf of Yara, it's an honor to award the prize to you. Congratulations.
Yes, hello. My name is Robert Wissing, and so first of all, I would like to thank the committee and Yara for awarding me this prize, and of course my supervisor for guiding me through the hard times of the PhD. Today I'm going to talk a bit about my thesis work and the background around it. But I was thinking that first let's go through the basics. So how are magnetic fields produced? Well, magnetic fields are produced by the motion of charged particles. So, and at the same time, when you have a magnetic field, charged particle will feel a force of the magnetic field bending their trajectories. So whenever you have charged particles, you will very likely also have magnetic fields. So magnetic fields and charged particles go hand in hand. And two of the most well-known astrophysical magnetic fields come, of course, from our solar system. So first, we have the Earth's magnetic field, which is generated from the liquid outer core, which is filled with charged particles that move around. This creates the magnetic field. And then we have the sun. And the sun, of course, is just a ball of charged particles. It's a plasma, right? So it forms its magnetic field from its interior motions. And the sun's surface is very unstable. So it very frequently erupts and sends out a big burst of charged particles out into space. Some of these, of course, goes towards the Earth, but the Earth, luckily, we have a magnetic field. So the magnetic field deflects these charged particles, and some of them are deflected in the polar regions, which excites the atmosphere and creates the beautiful aurora, or northern lights. And this was exactly what Bireland experimented with, right? So he set up, in his laboratory, he set up an experiment to simulate this sort of process. So he had a magnetic ball, or magnetized ball, which he shot rays of charged particle at, and looked at how are these deflected. And you can see here on the right picture that these, like the charged particle, when they hit the magnetic ball, they create this, basically, this light around the poles, which correlated very well with the aurora. So this is a very smart way to explain the aurora during his time. But now let's zoom out. So now let's look at the present day, because it turns out that galaxies are also magnetized, because most gas in galaxies actually contain large fraction of charged particle. And here to the right, we can see actually a picture from the Planck satellite, looking at basically the synchrotron radiation, which depicts the strength of the magnetic field. So we can see that magnetic field is very strong in the center, but that it flares out into the also circumgalactic medium. And here on the left, we can see the Whirlpool galaxy, which is taken with the Hubble telescope. And here it's a bit hard to see, but you can see the lines which shows the direction of the magnetic field. But it is basically along the spiral arms of the galaxy. And very surprisingly is that these magnetic fields are very strong compared to what we maybe initially thought, because if we make calculations of processes that can create the primordial fields very early on in the galaxies, we get a number of something like 10 to the minus 20 Gauss. But magnetic fields in galaxies is about 10 to the minus 6, or even higher in some very starbursty galaxies. So the magnetic field must have grown 10 to the 14 times stronger during the evolution of the universe. So this requires a fast growth of magnetic fields. So what kind of process can explain this? Well, dynamo. So dynamo theory is a way the magnetic field can grow exponentially fast. And dynamo only, in a sense, means that you're transferring kinetic energy to the magnetic energy. And basically an exponential, like a fast dynamo. An example of a fast dynamo is, I like to show this toy diagram, because what you do is basically you take a magnetic loop, you stretch it, you twist it, and you fold it. And then you get basically 2 times the magnetic field. And this is done by the underlying fluid motions. So what kind of fluid motions can do this sort of thing? Well, turbulence, of course. And I think this is very nicely depicted in this bottom picture. So we begin with just a vertical magnetic field. And then in this box, we have a turbulent field, which is basically twisting and tangling up the magnetic field, stretching it, twisting it, and folding it, which means that we have an increase in the magnetic fields. And we also saw, right, this ordered magnetic field in our galaxy. And for that, the rotation in the galaxy can actually help. Now, what is the role of magnetic field? Okay, so we have strong magnetic fields in the galaxies, but what does this mean? Well, the thing is that if we look at the energy content of the magnetic field and compare it to, for example, the thermal energy content, they are about the same, or even in some cases, the magnetic field seems to be even stronger. This means that they are very dynamically important. And this, I think a good example of this is, for example, if you look at the collapse of molecular clouds. So the collapse of molecular clouds is the first stage of the star formation process, because this is what creates the stellar nurseries. And if you have a strong magnetic field, this will basically hinder the collapse or slow down the collapse, resulting in less star formation. And this has a big effect when you do numerical modeling of the galaxy, of course. Second, it is also very important when it comes to cosmic rays. As Gunnar showed, he had an instrument where he had 2 magnets and cosmic rays coming in, right, and bending them. And so cosmic rays are released in supernova explosions. And these are highly energetic particles moving near the speed of light. And they will basically get trapped by the galactic magnetic field, and it is believed that they can potentially drive galactic outflows. Another role in magnetic fields is that we have found them around the accretion disks of black hole. And in theory, it is believed that the magnetic field, because of basically instability, increases the transport of material towards the black hole, making them brighter than what we would expect. And also magnetic fields is believed to be an essential component in the formation of astrophysical jets. Yes, so the goals of my thesis work was to basically develop a numerical model for galaxy simulation that can properly model magnetic fields, and apply this to methods that are, or processes that are very, very challenging. One case is the jet formation of the magnetized core collapse, and to capture the periodic magnetic field reversals present in accretion disks. And of course, explore the dynamo processes. And so what we want to do is basically create a virtual laboratory. Just like Bireland, right? He set up his system. We do so too, but we do it using computers. And so here is me sending commands to a big supercomputer cluster in Europe and letting it do the work, in a sense. Yes, but as was said, magnetic fields are very hard to properly model numerically. And this is why, actually, like we have done galaxy simulations for quite a while, right? But magnetic fields have never been added because they go unstable. They break down. So it's very hard. And I think 2 examples that show this very nicely is, for example, the magnetized cloud collapse, where you expect at the end of collapse to have the formation of a jet. However, you can see in the old model, there's no jet, right, in the left picture here. And another case is in accretion disks. So if we look at the side-on magnetic field in an accretion disk, we actually expect it to have magnetic field reversals. So the magnetic field goes from positive, negative, positive as time goes on. But when we simulate it with older models, we just get this, which is sort of a runaway growth of the magnetic field, so it goes unstable, basically. But now, with the new numerical model that I developed during my PhD, we can see that we can successfully capture jet formation, and we can see that we do capture the periodic magnetic field reversals in the accretion disks for a very long time. And this is the first particle method to ever do this in 3 dimensions. And I thought it would be interesting to actually just explain the magnetic structure around a jet. So here we can see a 3D render of a jet being formed. And here we can see the magnetic field lines, how they look at different radius, in a sense. So along the jet, we can see that the magnetic field basically points straight up along the jet. But then as we go further out, we can see the magnetic field basically coils around this jet. So basically like a coil gun, shooting it up, accelerating it up. And then we come to the galaxy simulations that we do. So here we have an isolated Milky Way type galaxies. We set up some initial field and then we let it run. And we can see how it develops. So first it's quite a weak field, but as it turns more red, it grows in strength. And you can see that the growth basically starts happening in the spiral arm structure. That's where you have large modes of turbulence being generated. And we ran 60 galaxy simulations with a lot of different varying setups because we wanted to test all kinds of different parameters. And what we find is, in many cases, the magnetic field amplifies very quickly, reaching saturation in about 1.2 gigayears. And this is in the paper, in the article, if you're interested, you can read a bit more. And we show that the dynamo processes are captured. And we see a very strong mean field dynamo, which is consistent to the classical theory of an alpha omega dynamo. And we can also see that during this movie, right, that the magnetic field was pushed out of the galaxy, basically magnetizing the whole circumgalactic medium. And further, we also have started to look at comparing this, also our simulations with observations now. So here is some observation of that you can see. So this is observation of with the radio telescopes, where they can basically, from the polarization, check the direction of the field. And you can see here is a side-on view of the galaxies, and the arrows go up, down, up, down, up, down. And then in our simulation, here, the blue is down, the red is up. So you have up, down, up, down, up, down. So a very similar pattern. So this work has increased our understanding of galaxies, because this is still very early, right? As I said, we have just recently started to add magnetic fields to galaxies. So this is first step, and thank you very much.
Thank you so much. We look forward to follow you in the years to come. And now, dear audience, it's time for this year's Bireland Lecture, and I call upon the Rector of University of Oslo, Svein, to announce the topic and introduce the lecturer.
Thank you so much. I'm happy to see so many people here. It's really excellent. And I would like to start saying thank you to Gunnar and Robert for excellent lectures. Professor Amundsen, when I heard your justification of the award, I was a little bit worried about the complexity. But then we saw this beautiful illustration, and you explained the advanced theory and mathematics lying behind. So I think this was excellent, really. So thank you so much. So distinguished speakers, ladies and gentlemen, fellow admirers of Christian Birkeland, it's a great week for space science in Norway and Oslo. Today, Dr. Jonathan Gardner. Tomorrow, we will launch a new Center for Excellent Research at the University of Oslo, the Center for Planetary Habitability, one of 5 new centers of research excellence at the University of Oslo after the last call from the Research Council. Long-term basic research. And the center we are going to launch tomorrow is driven by our human desire to understand the world and the cosmos, like what drives the scientists here today. And we do have a proud space science history in Norway and in Oslo. A history we are celebrating here tonight. And 2023 is, as all years, an excellent year for celebration of one of our greatest researchers and innovators, Christian Birkeland, physics professor at the University of Oslo. His life and work continues to fascinate us 106 years after his death. Birkeland was the first scientist to realize that the northern lights had something to do with electromagnetic storms from the sun. He was also responsible for 60 new patents, from everything from margarine and caviar to something more important, of course. The electromagnetic cannon is famous, of course, but of course he was also the man behind the fantastic invention that enabled the making of fertilizer by harvesting nitrogen from air. The discovery was the basis from the foundation of Norsk Hydro, the industrial bonanza at Notodden and Rjukan, and now, of course, also the basis for today's Yara. But most important, maybe, from our perspective here today, is perhaps also that he pioneered a new modus operandi for combining theory with experiments, with simulations, with calculations. And he also laid foundation for much of the modern research conducted in the field of space and solar physics. So he was certainly one of the first space scientists globally, and is still an inspiration to new generations of students and scientists in Norway. Today we are certainly also here to get inspired by today's distinguished Birkeland lecturer, Dr. Jonathan Gardner. Gardner received his PhD from the University of Hawaii. As a NATO fellow, he did postdoctoral research at the University of Durham in UK. He came to NASA Goddard in 1996 to work with the Hubble Space Telescope, but soon got involved in the studies of the Webb. His scientific research involves using deep infrared observations to study the statistical evolutions of galaxies. And on the Webb project, he works with other scientists to ensure the scientific success of the mission, now coming to our all's attention with the Webb's very early results, really. So in addition to this, his role on Webb, Gardner also served as the chief of Goddard's Observational Cosmology Lab from 2006 to the launch of the Webb on Christmas Day 2021. So today, Gardner is going to give us a lecture on the James Webb Space Telescope. And this telescope was built to provide answers to some of the universe's great mysteries. So, curiosity-driven, basic research, as well as to give humanity an understanding of our place in cosmos. It has already taken a number of amazing images of, among other things, stars being born, and has discovered some of the oldest galaxies ever observed. He will talk about the path that takes us through the universe's 13.8 billion year history, connecting particles and energy from the Big Bang to the formation of galaxies, stars, and planets. So, Dr. Gardner, Jonathan, the floor is yours.
Thank you very much for that very kind introduction. It is an honor to be associated with such a great scientist as Christian Birkeland. There's been a very good introduction to Birkeland's work from Dr. Wissing, and I don't need to explain the origin of the aurora that Birkeland described in his work. But I do want to say something that hasn't been said about Birkeland. As a person who grew up as a coin collector, I'm very excited to be associated with one of the very rare physicists who is depicted on the money, on the currency. Birkeland joins scientists like Newton and Galileo and Einstein in this. But I did want to show you the picture that Bireland was not able to see, the view of the aurora as seen from the International Space Station, seen from orbit around the Earth. So the astronauts get the privilege of looking down and seeing the aurora every time they go around the Earth when they're visible. Very beautiful pictures. So I will be talking about the James Webb Space Telescope. Webb is a 6.6 meter diameter space telescope. It is billed as the successor to the Hubble Space Telescope and NASA's previous infrared observatory, the Spitzer Space Telescope, which just recently finished its 18-year mission. Hubble, of course, is still going strong, and I do want to point out that Webb is the successor to Hubble, but it's not a replacement. We are thrilled to have the two telescopes both working at the same time and working together. It is Webb works in the visible light we can see, out into the infrared light that is where the wavelengths are too long for us to be able to see, but we also experience infrared light as heat radiation, and that will come back as an important aspect of how we designed Webb. It's the first time that NASA has used deployed optics, so we're folding out the mirror. The first time we've used that in the visible and infrared region. It is passively cooled to 218 degrees below zero. That's just 55 degrees above the coldest temperature there is, the absolute zero temperature. It was launched on Christmas Day 2021. It is designed from the very beginning to be complementary to all other telescopes, both telescopes we have in space and also the giant telescopes we're building on the ground. It is a joint project, an international project of NASA with the Canadian Space Agency and the European Space Agency. And Norway, of course, is an important part of the European Space Agency and contributed to the mission in that way. The lead is NASA's Goddard Space Flight Center, where I work. Our industrial partners are Northrop Grumman Aerospace Systems, Ball Aerospace, and the Space Telescope Science Institute, which is the operations center on the campus of Johns Hopkins University. This is the Hubble Ultra Deep Field, which until July of last year was the faintest picture that humanity had ever taken. It was taken with the Hubble Space Telescope, more than a month of observing time added up over time, and there's been almost a year of Hubble Space Telescope follow-up of this image. Now, why do we want to take a very faint image? Well, it's actually not for the beauty of the galaxies that we see in the foreground, but because we want to look backwards in time to when the universe was young. And we look backwards in time by finding things that are very, very far away, so far away that the light from these galaxies has traveled across the universe for most of the age of the universe. The universe is 13.8 billion years old, and these galaxies that Hubble was able to detect, the light was emitted when the universe was less than one of its 13.8 billion years. So that light has traveled for almost 13 billion years to get to us, and as it goes through the universe is changing. And this way we can look back in time to when the universe was young. So these very small, faint red galaxies, hardly resolved. When we studied them, when we followed them up with some of this additional Hubble time and with the Spitzer Space Telescope, we found something that was a little bit surprising. Although the light was emitted in less than 1 billion years after the Big Bang, these galaxies are fit by models that are several hundred million years old already. So to find the first galaxies that formed in the early universe, to set the initial conditions for the evolution of galaxies, how these first galaxies change over time to become galaxies like the Milky Way that we live in, we needed to go backwards further, further back in time, closer to the Big Bang, to see galaxies that are even further away. And that led us to design and build a telescope that went beyond Hubble in 3 very important ways. So the first one is that in order to see things that are further away, we need to see things that are fainter. We need to collect more light, and that means a bigger telescope. So Webb is 6.6 meters in diameter compared to 2.4 meters for Hubble. Now, in order to do that, we had to do something that was very complicated and very special. We had to fold the telescope up and fold the rest of the observatory around the telescope itself. As you can see, the size of the observatory, the size of the whole mission for Hubble and Webb are almost the same. Webb's just a little bit bigger, but the mirror is a lot bigger than Hubble's mirror. So we needed a bigger telescope. But we needed something else as well, because as the light is traveling for more than 13 billion years from those very distant galaxies to the present, to our telescope, the universe was expanding. This was a discovery by Hubble the astronomer, not Hubble the telescope. He found that the universe was expanding, and that was his big contribution to astronomy a century ago. And as the universe is expanding, this is an expansion of space-time itself, the light that is traveling from those galaxies gets stretched out by the expansion of the universe over this time. And light that was emitted as ultraviolet light, light that's too blue for us to see, or visible light, light from stars like our sun, is stretched out and moved into the infrared. So we needed an infrared optimized telescope. And as I mentioned before, infrared comes to us as heat. We can feel infrared as heat. And that means if you have a warm telescope, like the Hubble Space Telescope, a telescope at room temperature, the telescope itself is emitting infrared light, which will swamp the signal from the most distant galaxies. Hubble can see a little bit into the infrared, but we needed to see even further. So while Hubble is kept at room temperature, we needed Hubble goes in and out of daylight as it goes around the Earth every 90 minutes. And so we actually have heaters on board Hubble to keep it at a constant temperature, so it's not constantly going in and out of changing temperature. Also, when we send the astronauts up to do servicing of Hubble, we didn't want them to freeze to the side of the telescope. Webb, however, is allowed to cool to 218 degrees below 0 Celsius. That's 55 degrees above absolute zero. That's the warmest part of Webb. There are parts of Webb that are much colder than that. And we do this by putting it behind a tennis court-sized 5-layer sun shield that protects the Webb from the sunlight and allows all of the heat to escape from between those 5 layers. Another big difference between Webb and Hubble is that Hubble is in what's called low Earth orbit, 600 kilometers above the surface of the Earth. That's the highest that the space shuttle ever flew. And as I said, it goes around the Earth every 90 minutes, goes in and out of the daylight side, the nighttime side, lots of temperature changes and light from all different directions. But we put Webb in a special location called the second Lagrange point. It's 1.5 million kilometers away from the Earth. About 1 million miles. And the second Lagrange point is a special orbit worked out by Lagrange, the mathematician and astronomer, about 200 years ago, almost 200 years ago, in which the second Lagrange point follows the Earth as it goes around the sun, and the sun, the Earth, and the telescope, or the second Lagrange point, are always in a line. One way of thinking about it is that the L2 point goes around the Earth once per year as the Earth goes around the sun, always keeping those 3 points in a line. And this way, our 5-layer tennis court-sized sun shield will protect the telescope both from light from the sun and also the reflected light from the Earth and from the moon. This allows Webb to cool, keeps the Webb telescope in the dark, far darker than anywhere you can get on Earth, and allows us to see out in the infrared. Now, Webb is a large international project. There are literally hundreds of companies that contributed hardware to Webb across the United States, across Canada, and in many European countries. A joint project of NASA, the Canadian Space Agency, and the European Space Agency. And scientists from around the world are able to use Webb through a competitive process, writing proposals every year, including, I believe, Norwegian scientists have participated in Webb data. This is a family portrait of the cameras, the 4 cameras on Webb. We have the near-infrared camera, which works from gold-colored visible light. You might wonder why gold-colored. Well, we actually have gold-plated mirrors, so they reflect gold-colored light and go out into the infrared to 5 micrometers wavelength. For the near-infrared camera, takes many of the pictures that you've seen. The near-infrared spectrograph, which takes the light from each object and spreads it out into all of its wavelengths, and we can see the signatures of the atoms and the molecules that make up the item that we're looking at in the spectra. That is the European instrument. It was built by the European Space Agency with their industrial partners. The Canadians provided us with a camera that locks onto a bright star and keeps the telescope pointed where we want. And also on the back of that optical bench, they provided a specialized scientific capability designed to study distant galaxies and to study planets around other stars that we call exoplanets. And then last but by no means least, we have our mid-infrared camera, which does the longest wavelengths, tells us about the colder things in the universe, the most distant things, and the emission from molecules, including some organic chemistry, with our mid-infrared instrument. And that was a joint project of a consortium of European countries managed by the European Space Agency, working with the Jet Propulsion Laboratory in the United States that provided the detectors and a closed-cycle helium refrigerator that takes this instrument down to just 7 degrees above absolute zero. The assembly of the primary mirror was an innovation for space telescopes. There are ground-based telescopes made up of mirror segments like this, but Webb's primary mirror is made up of 18 hexagonal mirror segments, each 1.3 meters across, and each made of beryllium, which is a very lightweight, very stiff metal, and coated in gold. Gold is very highly reflective of infrared light, so we coated the mirror with gold and assembled the 18 mirror segments onto the back plane support structure, including the 2 side wings, which, as you will see, are folded back for launch. When the mirror was fully assembled, we took off those black protective coverings and had a photographer take this picture in the giant clean room at the Goddard Space Flight Center. One of the things that's really cool about this picture is that the photographer lined up the NASA logo on the back wall to be reflected in the Webb telescope primary mirror. And you can see that this is not a flat mirror. It is a curved mirror so that the logo is distorted. Also in front are some of the very proud technicians who worked on putting the mirror together. Now, I'm not in this picture because they don't let scientists in the clean room anywhere near the flight hardware. That's a job for very well-trained technicians. But in the back wall, you can see the viewing window where anybody can come in and look through the window and see the Webb telescope. And I was able to go in there at one time when the telescope was positioned such that I could take the coolest selfie I will ever take in my life. A picture of myself reflected in the 6.5-meter Webb mirror. Very exciting. So when the telescope was complete and the instruments compartment had been installed onto the back of the telescope, we took it down to the Johnson Space Center near Houston to do a cryogenic vacuum test, a very cold test of working in a vacuum, working the telescope at its operational temperature. This was done in a historic vacuum chamber, the Johnson Chamber A. It's on the National Register of Historic Sites because this chamber was built for the Apollo program, and the astronauts that walked on the moon practiced walking in vacuum in this chamber in their spacesuits. So when the Webb project took over this chamber, we took out the simulated lunar surface. We installed a liquid helium shroud in the inner inside the chamber to bring it down to the operating temperature of Webb. We went through a 3-month-long test. The first month was just cooling it down to its operating temperature. We had 30 days of testing, and then the last month, the last 30 days, was warming the telescope back up very carefully to room temperature so we could open the vacuum chamber. In the middle of this test, the Hurricane Harvey dropped 1.3 meters of rain on the Houston area within the course of about 2 to 3 days. There were literally heroes working to keep the Webb telescope hardware safe. We did not have to break the vacuum. We did not lose power. We did not have to warm up the telescope very quickly. And also, all of the people were kept safe. Although some of the people working on Webb, their houses were underwater while they were in there. Keeping our telescope safe. So there are heroes involved in this mission, and we honor those. So meanwhile, at the Northrop Grumman facility in Los Angeles, the company was putting together the 5-layer sun shield and the spacecraft. The spacecraft contains the rocket motors that keep it in position and the data handling and the transmitter back to the Earth. And then we installed the telescope and the instruments onto the spacecraft, as you can see here. Once that was done, we did a test of the deployment of the sun shield. Now, when tested on the ground, we have to have this table holding up the sun shield. In space, there's no gravity, and so it would deploy without that table. But as you can see, the deployment went well, and then we folded up the telescope ready for launch. So this is the launch configuration. The 2 side wings of the telescope are folded back, and the sun shield is kind of wrapped around the front and the back of the telescope. We then sent it down to Kourou, French Guiana, for the launch on the Ariane 5 rocket, and we went by boat. The telescope went by boat, or by ship, the MN Colibri, and you can see it going through the Panama Canal. There's a webcam. You can watch the ships going through the Panama Canal in the lower left. This picture is the last time that humans got to see the Webb Space Telescope before the rocket shroud was put around the telescope. And we then followed that on Christmas Day with the launch.
8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So that was the launch of the Webb on Christmas Day, a wonderful Christmas present for all of us who worked on the mission and for the whole world, in fact. And then about 30 minutes later, the Webb was sent off from the upper stage of the rocket, and Ariane had a camera to watch that go. So this is the last high-resolution image we have of Webb as it goes off 1.5 million kilometers towards the second Lagrange point. You can see the rocket is already over the east coast of Africa. That's the Gulf of Aden up there. Now, in the mission control room during launch, there was excitement and applause at the launch itself. But half an hour later, when we saw the solar panel pop out, this was an autonomous deployment popping out here just 30 seconds or so, or 90 seconds, sorry, after the separation from the rocket. That was when the people in the control room just went wild with cheering. Because we'd done a lot of practice runs of rehearsals of the launch and of the early days of the operations. And during these rehearsals, there was a group of engineers who were called the Rehearsal Anomaly Team, or the RATs. And the RATs would think up things that could go wrong that the team could then practice responding to. And one of the rehearsals, the RATs decided, we're going to make it so that the solar panel doesn't deploy, doesn't pop out, and see what the team does to try and, so people were working on waggling the telescope back and forth to try and knock it loose and so forth. But everyone in the control room knew that we only had 7 hours to get that out, or the batteries would go to zero, and that would be the end of the mission. So to see that just 90 seconds after the separation was extremely exciting. So following the launch and on its way to L2, we had 50 major deployments, and everything worked perfectly. There were 178 release mechanisms. Every single one of those release mechanisms fired properly and worked. The solar panel, as you saw, was deployed. It's providing nominal power. It needs about 1 kilowatt of power, and it can provide up to 3 kilowatts. The high-gain antenna, which communicates with Earth, that was deployed successfully, and we're using it once or twice a day to communicate. The mid-course corrections, these are firing the rockets to install it right into the perfect orbit that we needed. We got such a good launch out of Ariane, the Ariane 5, that we didn't have to use as much fuel for those mid-course corrections, and it means we have 20 years of fuel on board to maintain the life of the observatory, compared to the requirement that we had 10 years. So lots of fuel left over thanks to the perfect launch. The sun shield deployment also went perfectly. There are 140 release mechanisms, 70 hinge assemblies, 8 deployment motors, 400 pulleys, 90 cables totaling 400 meters. Everything worked perfectly. This was very exciting. I was doing shift work in the control room during some of this time period, and shifts meant you would work you would have an 8-hour shift, and I was on the midnight to I was on the midnight to 8 a.m. shift. The night before one of these deployments, the sun shield deployment happened, and at the end of my shift, I went went to sleep and woke up about 8 hours later, and they were saying, and it's finally able to go past the what they thought was a barrier. So they had spent that whole day very worried that it wasn't going to pull out, that there might be something in the way, that one of those covers hadn't quite gone far enough. And I woke up and they said, oh, it's now gone and everything's fine. So there was some excitement during the deployments, but everything in the end worked perfectly. The next deployment of the telescope We have the secondary mirror coming out on the spider, the instrument radiator, and then the two side wings of the primary mirror to make the full face of the Webb. Again, everything worked perfectly. And for me, I was on shift during the secondary mirror deployment, and of course this animation is sped up. This actually took about 15 to 20 minutes for that secondary mirror to come out. And the way the telescope works is the light comes from the very distant galaxies. It bounces off the primary mirror into the secondary mirror, and then down through the tube in the center of the telescope into the instruments. And I was thinking as the secondary mirror was being deployed, you know, what if something went wrong at this point and the secondary mirror didn't get into place? We would have those photons of light traveling for 13 billion years, bouncing off our telescope and going right back where they came from. But everything worked fine. The secondary mirror is in place. It does capture those photons and sends them into the instruments where we can learn about the galaxies that they're from. Now, we then had to go through a process of aligning the mirrors. The 18 mirrors, after the initial deployment, were not phased up as a single mirror. They were all it's like they were each independent telescopes, 18 different telescopes, and all of them out of focus. So we had to go through a process of lining up these mirrors. Each mirror was supported by 6 motors, so it can move in 6 different directions. That's back and forth and up and down, and we can tip it, we can tilt it, and we can rotate it to line each of the mirrors up with its neighboring mirror to less than to a fraction of the wavelength of light. There's also a 7th actuator that can poke the back of it and change the radius of curvature of the mirror segments. So the first thing we did was we pointed the telescope at a bright star and scanned across the sky and found 18 different images of that star from our 18 individual telescopes that were not yet working together. So then we moved the mirror segments so that they went into this array so we could see them and know which was which. And we went through the process of focusing each of those individual telescopes, bring it into focus so that it's working as 18 separate telescopes. And then we went through a process of stacking up these images on top of each other, again by moving the individual mirror segments so that that all of the images of the bright star line up. Now these are lined up, but they're not phased yet, so the telescopes are not working together. They're just stacked on top of each other. And this is the image that we took, and it looks a bit like a 1.3 meter space telescope would look. It's got all of the light from all 18 mirror segments, but they're not working together. To do that, we had to do an interferometric process where we took the light from 2 adjacent segments, and as we move one of the segments, the interferometry, the wavelengths, spread out, and we can get those mirror segments to within a wavelength of light of each other. The final process, the fine phasing, we use lenses in the near-infrared camera to take the telescope out of focus and sort of take an image, a picture of the mirror itself and see the differences to bring it down to essentially working as a perfect telescope. This last process is something that we do every 2 to 3 days. We do the measurement, and about once a month we find that there's been a little bit of a drift in one or two of the segments, and so we can move the segments back to phase up the mirror. This way, Webb is an active telescope. We can keep it working perfectly through the life of the mission. And in fact, we found that we were able to bring the mirror to almost twice the sharpness that was the spec. So this is the first image that we took by, again, pointing the telescope at a bright star And it surprised us because there were all these galaxies photobombing our picture of a bright star. And it should not have surprised us but what happened is that the optical engineers were simulating what the star would look like and the 6 spikes that come from the hexagonal structure of the telescope. And meanwhile, the scientists were simulating what galaxies would look like and putting together their pictures of galaxies. And somehow we just never talked to each other and said, you know, every time Webb takes a picture of anything, there's going to be galaxies, because we built this telescope to see galaxies, and it's really good at it. So, of course, this was not just autonomous. There was a very hardworking team, the Mission Operations Center, doing round-the-clock shifts. This is me up here, kind of in the back, and some of the other people at the time that we took this first picture and were able to see the first results. We then pointed the telescope at a field in the Large Magellanic Cloud full of stars, and we're able to tweak up the telescope so that it was giving a perfect image to all 4 of the instruments, not just the near-infrared camera. And one thing that shows you what we get with a 6.5-meter space telescope compared to the 0.8-meter Spitzer infrared telescope prior to that, this is the same wavelength, the same part of the sky. You can see that nearly 100 times better resolution gives you a really sharp picture of the universe. So it took about 6 months to turn everything on, phase up the telescope, and then test out all of the instruments. But by July 12th, we brought out the first picture, which was, at the time, the deepest picture of the universe that we'd taken in the infrared. This deep field is how we study distant galaxies. And we've done a number of these different fields, so I'm going to go to another one. This is the Cosmic Evolution Early Release Science Project, a large team that I'm a part of. You can see the images up in the up above, and kind of a zoom in on several of the bright, relatively nearby galaxies that you see. This one happened to have a supernova going off in the galaxy. You can tell because there's an arrow pointing to it. But that was a comparison to previous pictures taken with Hubble. But again, I wanted to illustrate what we have when we are looking in these deep fields. We want to look for things very far away, and we can identify the things that are very far away by their colors, and then get better data using the spectrograph, the near-infrared spectrograph. But as we zoom in through this picture, we're getting further and further away. The galaxies are actually getting smaller, and that's actually a physical result. The early galaxies are small, and they build up over time by merging together. But you see that as we zoom in, you find what was, when it was first identified, the most distant galaxy that we had known. That record has been broken since then. So there's another image showing where this galaxy is in the whole picture. And when we go to one of our other deep fields that had some low-resolution spectroscopy, this is the current record holder for the most distant galaxy. It's what we call a redshift of 13. That means that the light has been stretched out by a factor of 13 relative to the way it was the emission. And it is emitting its light just 325 million years after the Big Bang. That is 13.5 billion years ago. And this is the most distant galaxy that we have. Now, and several others in this field over that were emitting their light up to 450 million years ago. Now, these spectra, these are low-resolution spectra. We need to get higher resolution in order to really understand what's in these galaxies. This is a higher resolution spectrum of a galaxy that is a little bit more nearby. This is 430 million years after the Big Bang. And when we look at this galaxy, this says to me, as an astronomer, that we haven't done the job yet. We haven't found the first galaxies that formed in this area or in the universe, because this is a second generation. This has second generation elements. So the Big Bang produced hydrogen and helium and just trace amounts of lithium and beryllium, just the first 4 elements on the periodic table of the elements. Everything else was made in stars. So to find the first galaxies, we have to find galaxies that are made up of stars that only have hydrogen and helium in them. And in this galaxy, just 430 million years after the Big Bang, we have nitrogen, carbon, oxygen. There's the helium line. So it's got helium and hydrogen from the Big Bang, magnesium, neon, and so forth. So these heavier elements formed in the first generation of stars, and those stars, some of those stars blew up and distributed the elements around to the gas that would form later generations of stars. But this is such a good spectrum. It's so clear that I know that when we get more data, we will be able to find those first galaxies. Maybe some of the ones that I showed you, the low-resolution spectra, when we spend more time and get deeper spectra. But this all takes time. We have to get the images, we have to get the data, pick out the targets, and then go back with more time and the higher resolution spectra. So the process by which these first galaxies evolve over time, as I said, the first galaxies that formed are very small compared to present-day galaxies like the Milky Way. And over time, they build up by merging together and also by forming more stars within the galaxies. So in this nearby collection, there are 4 galaxies here that are at the same place. This is actually a foreground galaxy nearer to us. But those 4 are in the same place. They're a group of galaxies, and they're merging together. And one of the things you can see in the Webb data is that as these galaxies are colliding together, when galaxies collide, most of the space in galaxies is empty space between the stars. So the stars themselves don't bang into each other, but the gas between the stars does. This is another image of a nearby galaxy showing that with Webb we can pick out the dark regions, the dusty regions where stars are forming in visible light. That light doesn't get out, but in infrared light, the light does escape from does get through the dust, and we can see where the action is happening, where the stars are forming. This is a star-forming region much more nearby, and it shows the process by which the stars interact with the cloud of gas and dust where stars are forming. So the largest stars are pretty messy. They put out a lot of energy and a lot of both gaseous winds and also ultraviolet energy, which kind of blows a bubble in the surrounding cloud that is forming stars. So you see the bright star in the middle and the empty bubble where you can actually see through to what's beyond. But the edges here are where the winds from the bright star are impacting the cloud, and that shock creates new stars. So when we are studying star-forming regions, these dusty clouds, we have, this is a visible light image taken with Hubble of a very iconic, the Eagle Nebula, sometimes called the Pillars of Creation. And what we have going on here is that there's a very bright star kind of up here, shining light and blowing the dust away. But the very densest regions where new stars are forming can withstand that wind and hold their dust, and these are shadows of that. But when we go into the Webb near-infrared image, we can see through that dust to where the star formation is happening, where the stars are actually forming. And then when we go out even to longer wavelengths, the dust itself starts to emit light, and we can see the dust map, the dust in the mid-infrared image. These star-forming molecular clouds are nurseries of new stars and planets. This was one of our very first images, and as you zoom in, you can see stars are forming here. Star formation is a pretty messy process. It puts out a lot of gas in jets, as we heard about earlier. Here's another star-forming region and a jet that's coming out of that. And then when we go to mid-infrared spectroscopy, we can see the constituents that make up the stars and planets, the molecules. So we have a bunch of organic chemistry, and this is a spectrum of a low-mass new star where we can see things like methane. There is acetylene, a benzene ring here, 6 carbon atoms with their hydrogen atoms, carbon dioxide, and this is carbon dioxide, two oxygen and a carbon, and going all the way out to methyl, and a whole bunch of organic chemistry, a whole bunch of carbon chemistry that will provide the building blocks for the planets that will be around this star. Webb has also, although when we first wrote down the science goals for Webb 20 years ago, around 2003, 2004, we knew exoplanets, planets around other stars, were going to be important. We didn't know that much about them. At that time, there were only about 10 known planets that transit in front of their stars, but we knew that that was a great way of measuring the atmospheres of planets. So when a planet will pass in front of its star, as shown in this illustration, the light from the star actually goes through the atmosphere of the planet. Now, this is not a image of an extrasolar planet. This is actually a transit of the moon across the face of the sun, as measured by one of our sun-observing satellites. If that was seen from Earth, it would be a solar eclipse, and the moon would completely block the sun. But it's not observed from Earth, so the relative sizes. But it illustrates what happens when the planet blocks some of the light from the sun. The amount of light that we receive in our telescope goes down by a little bit, and we can determine the properties of the planet just by measuring the light and doing the math. And this was the first detection of carbon dioxide in the atmosphere of an exoplanet. One of the big goals for Webb is to find an Earth-like planet that has an atmosphere. This planet is actually a large planet like Jupiter. They're a lot easier to see, a lot easier to measure, and very interesting to find the whole diversity of what planets around other stars are like. But we would like to know about planets like the Earth, and so this is one measurement where we followed a transiting small rocky planet all the way around its star. So both when it's crossing in front of the star, but also when it goes behind the star, and we can actually see just the star without the light from the planet. And as it goes around, we go from the nighttime side of the planet facing us to the daytime side of the planet facing us. And by doing the math, we can determine the temperature on the surface of this planet. And so this was one of our exciting measurements where we were hoping to find an atmosphere, but turns out this particular planet does not have an atmosphere. It's too hot for that. But we're continuing to observe Earth-like planets, and again, just a bit more data. We hope to find exoplanets that would have small rocky planets, maybe planets that have that are in what we call the habitable zone, where the temperature is the right temperature for water to be liquid on the surface, like it is on the Earth, not steam like it is in the atmosphere of Venus, or frozen ice like it is on the surface of Mars. The habitable zone is what we call that region where the temperature is right for liquid water on the surface, which we consider to be important for life on Earth. There is, again, by taking spectra of exoplanets, we can see the organic chemistry, we can see water signatures, carbon monoxide, methane, and even silicate clouds on this planet. This is, again, a gas giant planet, but it's got clouds of silicates in its atmosphere. So then we get to our own solar system. Webb cannot point towards the sun, but it can look at all of the planets from Mars on out. And we did a detailed study of the Jupiter system, including very clear detections of the aurora on Jupiter. And this is the connection to Bireland. Webb has detected the aurora on all of the outer planets, the gas giant planets. The aurora, of course, being an interaction between the planet's magnetic field and the wind from the sun. This detection of Jupiter's aurora was so bright that it's actually got spikes from the optics. There's also, Webb is very good at detecting rings, and so while you might think Saturn's the only planet that has rings, they all have rings, all of the gas giants. So this is a detection of the rings of Jupiter. It's very small and faint compared to Saturn's and some of the inner moons of Jupiter. This is a picture of Neptune, and there is a team currently studying, writing a paper on the aurora of Neptune. That paper is being readied for submission, and a very nice detection of the rings of Neptune. Webb is a very good ring detector in the planets in the outer solar system. And here is a picture of Uranus with its Shakespearean moons. The moons of Uranus were named after mythological characters from English history instead of the standard that was for all other planets. And zoom in on this, again, a beautiful picture of Uranus with its multi-level rings, and this is the pole, so the aurora are right there. Uranus has got knocked on its side and is kind of pointing, I think it's the South Pole at us. So Webb has also had an impact on the public, on the people. There's a lot of excitement among the public for the Webb's discoveries and for what it can do, and for actually a large scientific project done by an international collaboration. We got pictures on the front page of the newspapers. Our first images were put on up in Times Square and Piccadilly Circus. Bands like Coldplay and Jimmy Buffett used Webb imagery in their own light shows. We had the Google Doodle, and the United States has a postage stamp with the Webb telescope on it last year, and they're going to be bringing out this fall additional stamps with actual Webb imagery. So if you'd like to follow along, we are putting out discoveries almost weekly. Every week or two, we have, of course, a website where you can go. There's a blog. I'm actually involved with some of the writing of the blog. The blog kind of takes things to a little bit of a deeper level than the public level of the press releases, does a bit more explaining of the science, a little bit more in depth. Our image archive is webbtelescope.org, and of course you can follow on social media. And as I said, we are bringing out new images almost every week. This was last Thursday's. It is a star, a newly formed star, and the two beautiful jets coming out of the poles, just like Dr. Wissing told us about earlier. So I'd like to thank you. As I said, it's a tremendous honor to be selected to give the Bireland lecture in his honor, and to be joined by a bright young scientist getting the prize with a very interesting talk earlier. And I would be happy to take any questions that you have. Thank you.
I take the liberty to come up here and just say thank you. I'm Jan Holt. I'm a chairperson of the Bireland committee, and since the Bireland lecture is invited by the Bireland committee, I, as chairman of the Bireland committee, is proud of the lecture we had today. It's fantastic. It's exciting. If we go back to 1994. We had the Winter Olympics in Norway, in Lillehammer, and in the closing ceremony, the president of the Olympic Committee said, "The best games ever." I am not allowed to say the best lecture ever, but I'm allowed to say probably the best lecture ever. So then we open up for questions.
Thank you very much. And Professor Holte has been a very kind host to me. He took myself and my wife around showing some of the sights of Oslo, and has been a very wonderful experience in my first visit to Norway. So are there questions?
What's the best way of getting at these images as a member of the public? Do you have something like where you can easily pan and zoom into the full resolution and switch frequencies in the browser without needing to download a big FITS file or something? Or
Yes, so the best way of getting the images, we have the image archive. As I said, it's webbtelescope.org, or you can go to our main website, web.nasa.gov, and click through the press releases. All of the images that we put out on these press releases or on the blog are processed by our graphics experts to show the science, to show the what's going on in the images, while also being beautiful pictures to look at. So it's all on our website. We are very careful to stay true to the science. Of course, we cannot see infrared, so we translate the infrared into visible light, but we keep the wavelengths in the same order. So the shortest wavelengths in the infrared are mapped to the blue, the middle wavelengths are mapped to the green, and then the longest wavelengths are mapped to red. So we keep that order when we are putting together the pictures for release to the public in the press releases. There is a lot of web raw data that's available through the archive, and people who have proficiency in image processing can download the data and play with it. We actually have not only our scientists doing that, but we have some citizen scientists, people out there who like to get the raw data and make their own, do their own processing of the images. That's a little bit more involved than looking at what we've put out through the press releases, but it can be fun for the amateur astronomers and the citizen scientists who are out there. But the best way is go to our image archive and just play around, look around the pictures.
Thank you for a fascinating lecture.
Thank you.
And also for an insight into how the process was and the troubles and so on. I have a question concerning the observations of bigger galaxies far into the beginning of the universe. Do you have a comment about that? And also, what's the sort of road ahead? What are the plans to look more carefully at them soon?
Okay, yeah, I think what you're referring to is that there was some discussion in the press that Webb was finding galaxies that were better formed than they should be at the time, and some people even kind of pushed that a little bit too far and said that it's challenging our understanding of the Big Bang. Well, I don't really believe that, but one of the more detailed results that we are getting in studying the distant galaxies is that the galaxies are more efficient at forming stars than most of our models predicted. Now, the very earliest galaxies are not very efficient at forming stars. Only about maybe 1% of the gas that's available in the galaxy will form stars that early on. So when we say they're more efficient than we expected, it's kind of more like 2% of the gas is being converted into stars. But this means that these galaxies are brighter than we expected. And of course, that's very exciting as an observational astronomer, as an observer, because it means they're easier to see and easier to study and easier to follow up with spectroscopy because they're brighter than we expected. There's more out there for us to see with Webb. So the process of studying distant galaxies, as I said, is doing galaxy surveys. And there are several things that we do. First of all, we almost always look in places that Hubble has already looked because we want the two telescopes to work together. We want the ultraviolet and the visible light from Hubble to go with the infrared light from Webb. Even the galaxies that we cannot see with Hubble, that's a very important scientific result, that if we have a galaxy that's well detected with Webb and is not there in the visible light, that means it's one of these very distant galaxies that are so far away that the ultraviolet light has moved all the way into the infrared. So we need Hubble to tell us that it's not nearby, not more nearby. So we always look in the places that Hubble has looked. Hubble's had a long time to set up a number of galaxy fields, deep survey fields. The other thing that we do is we have what we call a wedding cake approach to designing the surveys. We've got the big, wide survey that doesn't go as deep, but gets a large area, can get different environments, different densities of galaxies, and can find the rare, brighter galaxies. Then we have the middle layer of the wedding cake that's kind of deep and kind of wide, and then we go really long exposure in the one central area, the one central part where we have the longest exposures and we can see the faintest galaxies, and which on average are the most distant. Although there are some rarer objects that are very bright, and we get those in the wider surveys. So we've done the first generation of those surveys. The process for allocating time on Webb is through a competitive peer-reviewed annual process. So scientists from around the world write their proposals, put down their very best ideas, submit it to the peer review once a year. We have a multi-layered committee of almost 200 scientists involved in reading all of these proposals and picking the very best ones to do, because for our second year, we got 7 times as many proposals as we had time in a year to give out. So 6 out of 7 of the proposals had to be turned down. Some of them were very excellent ideas, which they can resubmit for the following year. But this competitive proposal process, we picked the very best science to do, and so we've now got the second generation. We've got the, we started the second year in July, a year after our first images were released. And that second year is the first observations that are based on following up what we discovered in the first year. So we had people discovering, the first generation discovered these very distant galaxies. Second generation is, let's go back and do spectroscopy, pick the best targets for the high resolution spectroscopy where we can look for the first stars that formed just from hydrogen and helium, for example. And then lots of other science. One thing I didn't mention too much was the role of black holes, but that's also very important to the story of galaxy evolution, because galaxies have giant black holes in their centers.
Very nice lecture, thank you.
So if I'm not mistaken, all of the images that I've seen so far released to the public, and none of them has been corrected for the PSF, for the instrumental PSF. Is it because we don't have a tool yet to accurately and reliably subtract the PSF, or is it in preparation?
Okay, so what the question refers to is that the telescope will spread out light even from a sharp star into an area around. And you saw that in the first image. We had the 6 spikes coming out that are part of the diffraction pattern, the point spread function, PSF, and then the spreading out of the light around the center of the star. And when we have a picture, there are techniques where we can deconvolve, we can take out those instrumental effects. But the problem is that only works when you've got lots and lots of signal from the star. Pictures of faint galaxies is very, very hard to take out the effects of the instrument and do sort of super resolution to resolve better than the perfection of the telescope. So we tend not to do that because that would just introduce artifacts and noise into the data. But there is one place where we do either subtract off the point spread function from the star to see, and that is when we are trying to directly detect light from exoplanets that are not transiting. So first of all, several of our instruments have a coronagraph, which puts a spot in front of the star to try to see the very faint planet right next to it to block out the light from the star. And when we do that, we not only put that spot in front of the star, but we also will take another image of another star that doesn't have a planet in the same place and subtract that off to try to pull out the light from the planet itself. The problem with studying exoplanets is that they're like a firefly next to a searchlight. There's a very bright star there, and the planet is maybe 1/1,000,000th of the brightness of the star. So you have to see the really faint planet next to the star. And there, that kind of deconvolution of the point spread function of the star will give you additional data. Whereas this kind of most of the things that we look at with telescopes, astronomical objects, there's not really enough signal to do that without introducing additional artifacts in the images. So we stay close to the original data. There are other fields like studying the sun where that kind of thing is, there's plenty of signal. And so they can do that. Well, thank you very much for your attention.